And we're back. Okay, this is the last type of chemical reaction we're going to be working with. This is called combustion. Combustion is a word we hear about a lot, and combustion are the fun ones. Typically because they result in a lot of energy change, which could be an explosion. Sometimes we see a fireball come out of it, but usually it's just a lot of energy, and it kind of depends on where it's contained. Okay, so we're going to see where that energy comes from and what the reactants and the products are. So before we get into what's behind me on the board, I'm going to show you this reaction because it takes a little while to let it kind of get ready to go. So I'm going to take some ethyl alcohol, some ethanol, okay, and this is a type of fuel. I'm just going to pour some into here. Okay, I don't need a ton, but I do need enough to make this reaction work. Hey, there's the bell. All right. So I'm going to take that now, and this is very similar to the bottle rocket we did at the beginning of the year. I'm going to pour it into this giant water jug. Okay, and what I really want to do is I want this ethanol to mix with the oxygen that's already in here. And we've talked before how the oxygen that's in this, there isn't as much as you think. Okay, oxygen is kind of limited. There's only about 20% of the air that's in there is actually oxygen. So what I'm going to try to do is I'm spinning this around because I want it to coat the inside of this surface on the bottle and then get it to evaporate as quickly as possible, as much of it evaporate as we can. So I'm just kind of spinning it around, hoping to spread it out and get it to evaporate quickly. Okay? And I'd like to take the leftover liquid and have it come out of there. I don't want it to be around. Okay? Now I look in there and I can't even see any alcohol left. So I'm going to add just a little bit more just to make sure that I got enough for this to happen. Okay, I'm going to dump just a little bit more in. And don't worry, I'm going to be able to take the excess out. So if I added a little too much, it's not the end of the world. But just adding more won't necessarily make this better. So I'm spreading it out. I want it to evaporate as much as I can and get it to mix with those oxygen molecules, but the reaction won't start until I add a little bit of activation energy. So I'm going to let this thing sit right here and drain. I want the liquid to come out and the gases to stay mixed in there. The gases are what's important. All right, take a look at the board and let's walk through this now. Combustion always looks the same. Okay? Combustion is a fuel added to oxygen gas, and there's lots of different kinds of fuels, but you're going to notice they all have carbon and hydrogen and oxygen in them. Okay? They have kind of the same stuff. Fuel plus oxygen gas, we add those together and then we get a little spark, or we get some kind of activation energy, and we get a huge reaction and a lot of energy released, and carbon dioxide and water vapor are the two components that come out of it. Okay? Now when we go to write this, this can be very easy to write because essentially the only difference in a combustion reaction with one type versus another type is what kind of fuel. All the rest of this is the same. Let's take a look at what those would be. Oxygen gas is one of those diatomics that we talked about that's always in pairs when it's by itself, so it's O2. Carbon dioxide, you guys know that as CO2. It's got the prefix there to help you. And water vapor is just water, it's just hot water. It's vaporized, so it's a gas. And the thing is, both of these come out of this reaction being very hot. So they expand and take up a lot of space, and that's usually what produces this explosion or this fireball sometimes that we see from it. Okay, now when I look at this, balancing these can sometimes be a mess. And mostly because this one has oxygen everywhere. So I basically want to ignore oxygen. I don't want to deal with oxygen until the very end. I'm going to take just the carbons and I'm going to work with those first and I'm see where it leaves me. So I've got 2 carbons here. And on this side I've only got 1 carbon. Remember that 2 only applies to the oxygen. So I have to balance the amount of carbons. I'm going to put a 2 in front of this. And now my carbons are taken care of. Okay, let's take a look at hydrogens. Remember, we're adding up all the hydrogens on the left side and combining all the ones on the right side, and then we compare those. There's 5 hydrogens plus 1 more. That's 6. Over here, I've only got 2. So if I put a 3 here, now my hydrogens are balanced. Now I want to take a look at this and go, okay, let's worry about the oxygens. We've got everything else taken care of. Let's look at all the oxygens over here. I've already put numbers in front of both of these. I don't really want to change them, so let's total these up. 2 times 2 gives me 4 oxygens. 3 times 1 gives me 3 oxygens. That's a total of 7. Those of you who are getting good at balancing immediately go, oh great, we have an odd number. This isn't going to work out well. Not necessarily. Be careful in combustion because I've got oxygen in multiple places over here. All I need is for this total between all of these to be 7. Okay, so if I were able to work backwards and go, well, if this one was a 1 and this was a 6, that would equal 7. So if I put a 3 here, that gives me 6 oxygens, plus that 1, now I have 7. This happened to work out because of that oxygen that was in the fuel. So you have to really be careful that you don't get in too much of a habit and you analyze what's there. That basically means I need 3 times as much oxygen as I have ethanol molecules in order to make this happen. And that's kind of hard to come by in our atmosphere, all in one place. So this has been draining for a while. And I'm going to take this out, and what I want to do before we shut the lights off is I'm going to light this little wooden splint, and then I'm going to hold it over the mouth of this and try to get just a few of those molecules to bang together real hard, to smash into each other real fast, start the reaction, and then it all should go from there. This is an example of a combustion reaction, very similar to what happens inside the engine of your car. Let me get this stuff out of the way. All right, here we go. Okay, and that's a typical combustion reaction. Now, when we did the bottle rocket at the beginning of the year, you saw the bottle rocket take off real fast. This one didn't, for 2 reasons. I have it sitting upside down, number 1. And number 2, this is a bigger space, so there was more room for those products to expand and get away from each other and sort of relieve that pressure, as opposed to some real small space. When this happens on the inside of a piston in your engine, it's such a small space that it really has a lot of force, and that's why we're able to drive. Okay, that's an example of a combustion reaction.